Hello, my name's Brock, and this is going to be a quick introduction to what a linked list is, why it's useful, and just what are certain things we could do with the linked list. Now, just to keep this video short, let's first define a linked list. So a linked list it's a collection of linked nodes. Could be sequential, it doesn't need to be. Typically, we think of them as sequentially linked nodes, especially when we're traversing them. So I guess it could be a sequential collection of linked nodes. What is a node? Well, a node really has two things. It has data contained within it, and it has pointers contained in it. Depending on what type of linked list you're using, here we're only going to worry about a singular linked list or singularly linked list, whatever it's hard to pronounce. So what that would look like is we would have some data and we would have a pointer to a node. So we could say this is our node, and it would have a pointer to a node. So we'll say node, and C++, we use a star to represent as a pointer, and we'll call it next. And then you could have another node of the node structure, and it could hold that data, and it will have that same node pointer pointing to a node called next. And what you'll do is and what we typically call the first thing in the linked node, like because it's sequential, we think of things being in order. This will be the head. And for every node that you add, it would just be the next. So that's why that next points to a node type, and we'll have it like that. And typically, you could just create more and more nodes until, well, you're done. There's different operations you can do to a linked list. You can insert things, you can add things like to the end, you could remove things. There's a lot of different implementations, but all we really want to do here is just, make it work in C++. So I'm just going to a random online compiler. Anything works as long as it is in some newer or any version of C. I don't know exactly what is an old enough version for this to not work. But anyway, let's define a structure. And this is what our node will be. So we'll just call it node. And within this structure, we can hold our data. Now we need to think of what data we're going to store. Let's just store like numbers 1 through 3. So int value or data. And then that other thing, the important thing, is the pointer. And it needs to point to a node. So we'll say node star to indicate that this is a pointer to a node. And we'll call this the next. And just we can make things easier by defining a constructor for a node. So in instructs, you can make constructors. And let's have it take an argument of value, okay? And then defined in the structure, in the constructor, we'll say data will be value, and the next will be set to null pointer by default. Let's get rid of that, okay? So we have our structure defined. So let's make a node. So back to typically what we call the first node in a linked list is a head. So we'll say a pointer of a node, pointer to a node called head, and we need to make a new node. So we're calling that constructor, and let's just pass the value 1. I always forget to end my semicolon for structure. Okay, so the program didn't do anything as expected, but it did compile. So now we could actually look at that value for head. So since this is a pointer, we're going to need to use this arrow operator to look at data. And well, let's see what the value is. So we could call cout, and we get the first value. Now, this isn't really a list. It's more of just a very convoluted structure. Okay, but let's actually add a second value. So how would we add a second value? I mean, we just call the constructor. So node, we'll call this second value, or just second, and let's call that constructor. Call it node. Accidentally press insert, and we'll set it to 2. So here we made a new node called second, and I guess we could cout seconds data. I have 1, 2. Perfect. The problem is this isn't linked yet. So what we need to do to link it, if you look back here, is we need to have that next pointer for the head point to the second node. So we could just redefine what head's pointer is. Okay, so we could say head, and its next, which is a pointer to a node, will now be set to second. Okay, and now instead of directly referencing second, we could just reference heads next. It's kind of confusing, but so let's cout, and we're going to say, okay, let's look at the heads next node, which is now pointing to second, right, from line 18. And we want to look at the value in there, and that should be 2. So we could comment out this cout, and it should print out 2, unless I made a mistake. Oh, it's not value, it's data. And we output 2. So what this is doing, just stepping through, so our main function at line 14, we're going to define a pointer to a node called head. Now within head, we have our default, or our constructor, which will create a node with the value, the data being set to what the argument is, or the parameter, which is 1. And then we're going to make a second node, a second pointer to a node called second, using the constructor setting the value to 2. And right from this line, on line 18, this is where we link it. We set the heads next, we set heads next, which is a pointer to a node, to second. And remember, second is a pointer. So in line 20, what we're doing is we're looking at heads next, which points to second, and we're getting the data. That's why we output 2. Now, of course, this isn't really the best way to do this. This is just simply having nodes. Now, typically, if you wanted to create a more, I guess, realistic linked list, we would contain all of this in a class called a linked list class, and then you could define your operators, which are, insertion, deletion, traversal, searching, I guess elimination, like deletion of the list, removal of objects, search, like they're organizing objects. There's all sorts of things you can do with the linked list, but typically in C++, you would define all of that in a class, and you would have within class a member called node, or some object or some structure called a node. Or yeah. But we're not going to implement that. So I guess let's just talk about why you would want to make a linked list. Because if you've been using arrays for a while, or vectors, you might sort of think, why is this better? Well, it's not always better, and it's not always better, and it's not always worse. Like a lot of things, these data structures have benefits and downsides. So I guess the biggest benefit here is how insertion and deletion works. If you're familiar with vectors in C++, how they operate is they're looking for data, within your memory. So how could I draw this? If you're looking in your memory as just some really long continuous piece, what a vector will do is it will create an object, or create a continuous piece of data, and it'll say, okay, I want this to be, element 1, 2, or 0, 1, 2, 3, 4. The back isn't working. 3, 4, 5, and so on. And this would be our vector. And the benefit of this is when you're trying to recall information from it, all it really needs to do is know where the head is, and then based on that address and based on how many bytes each piece of data takes, you can basically say, well, if the head address of this vector is like in registry 5, and each object takes 1 byte, very simple. And then you want to look at the 5th, you would just take 5, go plus 5, you look at now the 10th address, and that's how you would recall it. And it's very fast. It's pretty much continuous or constant in time. No matter where you're trying to look in that vector, it's always going to instantly return. But the downside is when you want to add something new, right? So when you make a vector, typically C++ will determine how large the vector needs to be, and that's all done, behind the scenes. But the problem is you can only make it so large. It can't be infinite in size. So let's say it has 9 elements. Well, what if you want to add a 10th element? Now, with the vector, you don't have to define how large it is, and you could just keep adding. Well, what it does is every time it needs to add something larger than how large the current vector is, it's going to look somewhere else in the memory and be like, well, I need some sequential piece of data or some continuous piece of data that has at least, and normally it doubles from the last value, if I remember correctly. So it'll look like, oh, where's 16 sequential bytes of data, something like that. Probably a bit larger, but anyway, that's what it would do, depending on the size of the values and the vector and whatnot. And that is the problem. Also, if you're trying to insert something into the vector, what it has to do is it has to go, okay, so from 1, 0, 2, and then it makes that new value 3, and then everything from 3 to 9 from the old list, it has to go one by one and assign it to each value, and it becomes very slow, right? Now, the advantage with a linked list is, well, first, we don't really need it to be sequential anymore. So let's say we had those 3 values. So in our memory, we have that value 1, which could be anywhere, wherever's free. So we'll say the head. And that head only needs to be as large as that structure is. That's one downside. With a linked list, you need that extra bit of data, the overhead, to contain the reference to the next object, but most of the times it's pretty small. And then you could say, well, okay, let's create that second object or that second node. It could be anywhere in memory, wherever's free. So we'll just say it's here. So that's second. So then we'll say, okay, well, let's make another thing called third. And that's there. It doesn't need to be sequential. That's one cool thing memory-wise. So then from head, you're pointing to second, and then from second, you're pointing to third. And then third doesn't point anywhere. Now, the cool thing about this is if you want to add another piece of data, you don't need to look for a sequential piece of data. You just need to look for data that's large enough to hold a node. So it could be anywhere that is free. So you just make fourth. So insertion is quite quick. And it's the same thing with deletion and removal of nodes. It's very quick in that you don't have to worry about shifting everything and things like that. And the downside, though, is you can't recall data quickly how you can with a vector. With a vector, you're just looking at the head of the vector, the address of the first object, and then thinking how many bytes is each, and then you're just adding that and then looking at that address. With linked lists, it's actually pretty bad. It's on linear time based on how many objects you have, right? So if you have 5 objects, or let's say we have 4 objects here, like 4 nodes. To get the 4th node, you have to first look at the head, then look at where the head is pointing, which is the second, look at where the second is pointing, the third, and look at where the third's pointing, the 4th. So retrieval of data is slow. However, adding data is quite fast, which is the opposite for vectors. Retrieval of data for vectors is quite fast. However, adding data can sometimes be slow depending on if you have enough memory. So that's what I wanted to talk about. I guess in another video, we could actually create a class called a linked list. Instead of just creating each node individually, we could contain all the operations that a linked list would have in a class. But that's for another video.